April 6, 1917. War Department, Washington, D.C. When President Woodrow Wilson signed a declaration of war against Germany, Colonel Edward Deeds, chief of the Army Aircraft Production Board, faced a crisis more fundamental than the shortage of aircraft or pilots. America needed to build thousands of warplanes, but the material those aircraft would be made from didn't exist in the United States. Germany's Zeppelins and advanced aircraft used duralumin, a revolutionary aluminum alloy discovered by German metallurgist Alfred Wilm in 1906 that was as strong as steel but weighed one-third as much. Duraner Metallwerk AG held Wilm's patents and had licensed production only to select European companies. America had been explicitly excluded. The Aluminum Company of America, Alcoa, America's sole major aluminum producer, had tried for years to replicate duralumin without success. The German patents were deliberately vague, describing chemical compositions but omitting the critical heat treatment process that made the alloy work. Alcoa's metallurgists, despite analyzing captured samples, couldn't understand why German aluminum hardened over time while American aluminum remained soft. Without high-strength aluminum, American aircraft would be built from wood and fabric like obsolete British biplanes, slow, fragile, and unsuitable for modern aerial warfare. The Liberty engine program could produce powerful motors, but airframes to carry them required materials America didn't have. This is the documented story of how Alcoa metallurgist Earl Blough and researcher Paul Merica cracked the mystery of age-hardening aluminum, creating alloy 17S that would become the foundation of American aviation and remain in production for over a century as aluminum alloy 2017. The story of aviation aluminum began not in a factory but in a Prussian military research facility at New Babelsberg, southwest of Berlin, where Alfred Wilm, 1869 to 1937, worked as a metallurgical engineer. In 1903, the German War Munitions Supply Department tasked Wilm with developing a lightweight aluminum alloy for military cartridge cases. Brass cartridges were reliable but heavy. Aluminum cartridges could reduce soldier load substantially if they could match brass strength. Wilm experimented systematically, testing various aluminum-copper combinations. Pure aluminum is too soft for structural use. It deforms easily and lacks tensile strength. Adding copper improved hardness, but not enough. The alloys remained too weak for military applications. Then, on a Friday in 1906, Wilm performed what seemed like a routine test. He heated an aluminum-copper-magnesium alloy to approximately 500 degrees Celsius or 932 degrees Fahrenheit to dissolve the copper and magnesium uniformly throughout the aluminum matrix, a process called solution heat treatment. He then quenched the sample rapidly in cold water to lock the elements in place. Standard metallurgical theory predicted the quenched alloy would be harder than before heating, but when Wilm tested the sample immediately after quenching, it was disappointingly soft, softer even than the starting material. Frustrated, he set the sample aside and went home for the weekend. On Monday morning, Wilm returned to find something inexplicable. The sample had become significantly harder. Over the weekend, sitting untouched at room temperature, the alloy had strengthened dramatically without any additional treatment. He conducted tensile tests. The tensile sample showed tensile strength exceeding 370 megapascals, comparable to mild steel, yet the alloy weighed just 2.8 grams per centimeter cubed. Steel weighs 7.85 grams per centimeter cubed. The strength-to-weight ratio was revolutionary. Wilm had accidentally discovered age-hardening, also called precipitation hardening, a phenomenon where aluminum alloys spontaneously strengthen over time after solution treatment and quenching. The mechanism would take decades to fully understand, but the practical result was immediate. Aluminum could be made as strong as steel. Wilm patented his discovery in 1906 under German patent DRP 244554. By 1909, he had refined the alloy composition to approximately 4% copper, 0.5% magnesium, 0.5% manganese, balanced aluminum. Duraner Metall Works AG in Düren, Germany, began commercial production in 1910, naming the alloy Duralumin, after the city and the metal's exceptional durability. Duralumin's first major application wasn't aircraft, it was airships. Count Ferdinand von Zeppelin's rigid airships required lightweight structural frameworks strong enough to support massive gas envelopes and control surfaces. Early Zeppelins used aluminum framework, but pure aluminum's weakness limited size and payload capacity. When Dürener Metallwerk introduced Duralumin in 1910, Luftschiffbau Zeppelin immediately recognized its potential. By World War I, German military Zeppelins used Duralumin extensively for structural frames, engine mounts, and control surfaces. The alloy's strength enabled larger airships carrying heavier bomb loads, the terror weapons that raided London starting in 1915. Germany produced approximately 750 tons of Duralumin in 1916 alone to support Zeppelin construction. Nearly 100 military airships were built during World War I, most incorporating substantial Duralumin components. But the alloy's true revolution came with fixed-wing aircraft. Professor Hugo Junkers at his Dessau works recognized that Duralumin could enable all-metal aircraft construction. Wood and fabric, standard materials for World War I fighters, rotted in weather, burned easily, and weakened with age. Metal promised durability, fireproofing, and structural integrity. In 1917, Junkers designed the Junkers Ji sesquiplane, an armored ground attack and reconnaissance aircraft featuring an all-Duralumin monocoque fuselage and wings. This represented a breakthrough in aircraft construction. The corrugated Duralumin skin served both as covering and primary structure, eliminating separate internal frameworks. The Ji entered service in March 1918 and proved remarkably survivable. Its Duralumin construction absorbed battle damage that would have destroyed fabric aircraft. Ground fire that punched through canvas and shattered wooden spars merely dented metal. Pilots who would have burned in fabric-covered fighters flew home in damaged Jis. Germany understood they possessed a strategic material advantage. Duralumin patents were military secrets. Licensing for foreign production were carefully controlled. When war began in 1914, German authorities immediately prohibited Duralumin exports to potential enemies. Britain received limited quantities through peacetime licensing to James Booth & Co., used primarily for the ill-fated rigid airship program. France obtained licenses through La Sociedad de Duralumin, which began production in 1911. But the United States, not party to pre-war European alliances, was explicitly excluded from licensing agreements. When Merica entered World War I in April 1917, it had no Duralumin, no licenses, and no legal means to produce the alloy that German and French aircraft already used. The Aluminum Company of America had tried to crack Duralumin's secrets for years. Founded in 1888 as the Pittsburgh Reduction Company, Alcoa by 1917 was America's dominant aluminum producer, virtually a monopoly. The company manufactured aluminum sheet, plate, rod, wire, and castings, but all from relatively soft, low-strength aluminum alloys. When German Duralumin appeared in 1910, Alcoa recognized the competitive threat. European aluminum companies licensed Wilm's patents and began producing high-strength alloys. Alcoa, excluded from licensing, was left with obsolete technology. In 1911, Alcoa metallurgists made laboratory heats, small experimental batches, trying to replicate Duralumin by analyzing published patent descriptions. The chemical composition was documented: aluminum with approximately 4% copper, 0.5% magnesium, 0.5% manganese, traces of silicon. Alcoa mixed these elements, melted them, cast ingots, rolled sheets, and tested the results. The material was strong, stronger than pure aluminum, but nowhere near Duralumin's performance. More frustratingly, Alcoa's alloys didn't age harden. They remained the same strength immediately after quenching as weeks later. Something was missing. The German patent described compositions but provided minimal detail about heat treatment, the temperatures, quenching rates, aging times that made age hardening work. These were Wilm's industrial secrets, deliberately omitted from patent filings to protect German advantage. Alcoa executives grew increasingly concerned as Europe's aluminum industry pulled ahead. British, French, and German companies were developing aerospace alloys, while Alcoa remained stuck with commodity aluminum for cookware and construction. Then the United States entered World War I, and Alcoa's frustration became a national crisis. In May 1917, the Aircraft Production Board calculated America's aircraft aluminum requirements, tens of thousands of tons of high-strength alloy needed within 18 months for the planned expansion to 22,500 Liberty engines and corresponding airframes. They turned to Alcoa. The company responded honestly, "We don't know how to make it." The War Department, desperate, authorized Alcoa to obtain Duralumin samples from any source and reverse engineer them without regard to patent law. Enemy patents had no legal force during wartime, but that didn't solve the technical problem, understanding how the alloy worked. Alcoa sent samples to the National Bureau of Standards in Washington, D.C. for detailed analysis. Dr. Paul Merica, a bureau metallurgist, led the investigation. Merica had trained in metallography, the microscopic study of metal structure, and approached duralumin systematically. Merica cut samples into thin sections, polished, etched with acid to reveal grain structure, and examined them under high-magnification optical microscopes. He compared freshly quenched samples, soft, with aged samples, hard, looking for microstructural differences. What he saw was revolutionary. Tiny particles, invisible to the naked eye, but visible under magnification, distributed throughout the aluminum matrix in aged samples. These particles hadn't been present in fresh samples. They had formed during aging, precipitating out of the supersaturated aluminum solution over days at room temperature. In a landmark 1919 paper published in the Bulletin of the AIME, American Institute of Mining Engineers, Merica, Waltenberg, and Scott proposed the mechanism. 1. Solution heat treatment, 500 to 520 degrees Celsius, dissolves copper and magnesium uniformly in aluminum. 2. Rapid quenching locks elements in supersaturated solid solution, unstable but frozen. 3. Natural aging, room temperature, days, allows copper-aluminum compounds, theta phase, Al2Cu, to precipitate as nanoscale particles, and these particles block dislocation movement in the crystal lattice, dramatically increasing strength. Merica had explained age hardening scientifically for the first time, but understanding the mechanism didn't immediately enable production. Alcoa still needed to develop manufacturing processes, determine optimal compositions, and scale up from laboratory batches to industrial tonnage. That challenge fell to Earl Blough, an Alcoa metallurgist working at the company's research facilities. Earl Blough, dates uncertain, records fragmentary, was an Alcoa researcher specializing in aluminum alloys. In 1917 to 1918, under intense wartime pressure, he led the team developing America's Duralumin equivalent. Using Merica's insights into age-hardening mechanisms, Blough systematically varied alloy compositions and heat treatments. He tested hundreds of combinations, measuring tensile strength, yield strength, hardness, and ductility for each. The challenge was balancing competing properties. More copper increased strength, but reduced ductility and corrosion resistance. Magnesium improved strength and aging response, but complicated casting. Manganese refined grain structure, but added cost. Silicon appeared in trace amounts, partly from impurities, and influenced precipitation. By 1922, Blough had developed a composition that met military specifications: Alcoa 17S composition, aluminum, balance 93%, copper 4%, magnesium 0.6%, manganese 0.6%, silicon 0.5%, iron less than 0.7% impurity. The 17 designation indicated the development sequence. Alcoa tested many compositions before settling on 17. The S indicated sheet form, the primary product form for aircraft construction. Heat treatment process: 1. Solution heat treatment, 500 degrees Celsius for 1 to 2 hours. 2. Water quench, rapid cooling to room temperature. 3. Natural aging, 4 to 5 days at room temperature to reach T4 temper. Properties of 17S-T4: tensile strength 380 to 430 megapascals, 55,000 to 62,000 psi. Yield strength 240 to 310 megapascals, 35,000 to 45,000 psi. Elongation 15 to 20%, reasonable ductility. Density 2.79 grams per cubic centimeter. These properties were nearly identical to German Duralumin. Blough had succeeded. Merica now had its own age-hardening aluminum alloy. But the timing was unfortunate. World War I ended in November 1918 before 17S reached full production. The Liberty aircraft program was largely canceled. Thousands of engines sat in storage. The massive aluminum expansion never materialized. Alcoa, however, continued 17S development through the 1920s. The alloy found applications in the few military aircraft built during peacetime, and, more importantly, in the emerging commercial aviation industry. The first major American application of 17S was the USS Shenandoah, a rigid airship built by the U.S. Navy starting in 1922. The Shenandoah used 17S aluminum alloy extensively in its structural framework, girders, rings, and cross-bracing that supported the massive helium gas cells. This was America's first major deployment of age-hardened aluminum in aerospace. The airship was christened September 4, 1923, and conducted numerous successful flights through 1924-1925. At 680 feet long, it was one of the world's largest aircraft, demonstrating 17S's capability to support huge lightweight structures. Then, on September 3, 1925, disaster struck. While flying through severe thunderstorms over Ohio, the Shenandoah encountered violent updrafts that exceeded the airship's structural limits. The framework, though properly designed and built, couldn't withstand forces from 5,000 foot per minute vertical air currents. The Shenandoah broke into 3 pieces at 6,000 feet altitude. The forward section crashed, killing Commander Zachary Lansdowne and 13 crew. The middle and aft sections, partially buoyant, descended more slowly, allowing 29 crew members to survive. The disaster wasn't caused by aluminum alloy failure. The 17S framework performed as designed. The airship's destruction resulted from encountering meteorological forces no rigid airship could survive. But the crash ended America's rigid airship program and shifted focus toward heavier-than aircraft, airplanes. This timing proved fortunate for Alcoa. The airline industry was emerging, and every aircraft needed aluminum. The late 1920s and 1930s saw aluminum transform from experimental material to standard aircraft construction. Donald Douglas, founder of Douglas Aircraft Company, pioneered all-metal commercial transports. The Douglas DC-2 (1934) and DC-3 (1935) used aluminum alloy extensively, not just 17S, but an entire family of aluminum alloys developed through the 1920s. 17S, or 2017, sheet and plate for fuselage skins and wing skins. 24S, or 2024, developed mid-1920s, higher strength for structural members. 61S, or 6061, non-heat treatable alloy for welded components. The DC-3 revolutionized air transportation, and aluminum made it possible. A typical DC-3 contained approximately 2,200 pounds of aluminum alloy, mostly in 24S with significant 17S content. The airframe could carry 21 passengers at 180 miles per hour for 1,500 miles, performance impossible with wood and fabric construction. By 1940, when World War II threatened, America's aluminum industry was the world's most advanced. Alcoa operated mills across the country, producing hundreds of thousands of tons annually. The company had expanded beyond 17S to develop 2017 17S, still used for rivets, screws, and structural members. 24S, or 2024, higher strength for wing spars and fuselage frames. 7075, developed late 1930s, highest strength for highly stressed components. 6061 or 61S, general structural weldable. Germany still used duralumin, Britain used hydrominium alloys, but American alloys equaled or exceeded them. The early disadvantage from 1917 had been overcome through systematic research and industrial investment. When World War II began, America was ready. Between 1940 and 1945, American aircraft production exceeded 300,000 military aircraft. Nearly all used aluminum alloy airframes, and 17S, or 2017, remained a critical component. While newer alloys like 2024 and 7075 provided higher strength for primary structures, 17S excelled in specific applications. Rivets. 2017 T4 rivets were standard fasteners throughout American aircraft. The alloy's moderate strength and excellent ductility made it ideal for joining higher strength structural members. A single B-17 bomber contained approximately 400,000 rivets, most aluminum alloy. Fasteners. Screws, bolts, and other hardware used 2017 extensively. The alloy could be machined to tight tolerances and threaded without cracking. Forgings. Engine mounts, landing gear components, and control surface fittings used 2017 forgings where moderate strength and good corrosion resistance were required. Structural members. Secondary airframe structures, ribs, bulkheads, fairings, used 2017 sheet and extrusions. By 1943, Alcoa's production capacity reached extraordinary levels. Sheet and plate 850 million pounds annually. Extrusions, 120 million pounds annually. Forgings, 70 million pounds annually. Of this, 2017 represented approximately 15 to 20% of total tonnage, still hundreds of millions of pounds supporting aircraft production. The Cleveland Works facility, expanded in 1943 to 1944 to 10,300 employees, became the world's largest aluminum forging plant. Much of its output was 2017 forgings for propeller hubs, engine components, and structural fittings. Alcoa's wartime aluminum enabled aircraft like the B-17 Flying Fortress, 2,200 pounds of aluminum per aircraft. The B-24 Liberator, 2,400 pounds of aluminum per aircraft. The P-51 Mustang, 840 pounds of aluminum per aircraft. The C-47 Military DC-3, 2,200 pounds of aluminum per aircraft. The material that didn't exist in America in 1917 had become so abundant by 1945 that aluminum airframes were standard. Nobody questioned whether aircraft should be metal. The only question was which aluminum alloy to use where. Post-war research finally explained completely what Wilm had discovered accidentally and Merica had theorized correctly. Using transmission electron microscopy, developed during and after WWI2, metallurgists observed precipitation at the atomic scale. When aluminum-copper alloys age at room temperature, the following sequence occurs. Stage 1. 0 to 4 hours. Copper atoms cluster in aluminum matrix, forming GP zones, Guinier-Preston zones, copper-rich regions just a few atoms across. These create lattice distortion, slightly increasing strength. Stage 2, 4 hours to 4 days. GP zones transform into theta-2 precipitates, coherent particles of approximate composition Al2C, still maintaining crystal continuity with aluminum matrix. These cause maximum strengthening, peak aged condition, T4 temper. Stage 3, weeks to months, theta-2 transforms to theta-1 precipitates, semi-coherent particles that are more stable but provide less strengthening. Overaging has begun. Stage 4, years, eventually theta-1 converts to theta precipitates, incoherent particles providing minimal strengthening. The alloy is now overaged and soft. This explains why Wilms samples strengthened over a weekend. Theta-2 precipitation occurred during that time, reaching near peak strength in 4 to 5 days. It also explains why Alcoa initially failed to replicate duralumin. Without understanding aging kinetics, they likely tested samples too soon, before precipitation, or too late, after overaging, missing the peak strength window. The science validated Merica's 1919 insight. Microscopic particles block dislocation motion, increasing strength. The discovery earned Merica recognition as one of the fathers of physical metallurgy, and age-hardening aluminum became a foundational technology of modern material science. After World War II, the alloy designation system changed. In 1947, the Aluminum Association standardized nomenclature. 17S became 2017 under the new 4-digit system. First digit, 2, copper is primary alloying element. Second digit, 0, original alloy, not a modification. Last 2 digits, 17, identify the specific alloy. The 2000 series became the age-hardening aluminum copper family descended from duralumin and 17S. Other alloys in this family include 2014, forgings, plate, 2017, 17S, rivets, screw machine stock, 2214, aircraft structures, high strength, and 2219, cryogenic applications, weldable. 2017 T4, solution heat-treated and naturally aged, remains a standard rivet and screw machine alloy today. It's used in aircraft fasteners, still specified in aerospace standards, automotive components, drive shafts, screw machine products, consumer products, camera parts, small mechanisms, and marine hardware, corrosion-resistant fasteners. The alloy Earl Blough developed in 1917 to 1922 is now over 100 years old and still manufactured globally. Annual production exceeds thousands of tons, primarily for aerospace and transportation. Without 17S and its descendants, modern aviation wouldn't exist. The strength-to-weight ratio of age-hardening aluminum enabled commercial aviation. Jets like the Boeing 707, 1958, 747, 1969, 787, 2011, all use age-hardening aluminum alloys descended from 17S technology. Military aircraft. Every fighter, bomber, and transport since World War II has incorporated 2000 series alloys for structures and fasteners. Space exploration. The Apollo lunar module used aluminum alloy 2024 extensively. The International Space Station contains thousands of 2000 series components. Automotive lightweighting. Modern cars increasingly use aluminum to reduce weight and improve fuel economy, all enabled by age-hardening technology discovered in 1906 and developed industrially by Alcoa after 1917 to 1922. The global aluminum industry, now worth over $150 billion annually, traces directly to Wilms' 1906 discovery and Alcoa's 1917 to 1922 development of 17S. In April 1917, America entered World War I without the aluminum alloy necessary to build modern aircraft. German Duralumin was a military secret. British and French producers were licensed, but America was excluded. Alcoa had tried for years to replicate the alloy without understanding the age-hardening mechanism that made it work. Within 5 years, that disadvantage was overcome. Paul Merica explained age-hardening scientifically. Earl Blough developed 17S as America's equivalent to Duralumin. By 1922, Alcoa was producing high-strength aluminum alloy commercially. The timing meant 17S missed World War I. The Liberty aircraft it was meant to enable were largely canceled, but it arrived perfectly for commercial aviation's birth in the 1920s and military aviation's explosion in World War II. Today, when aluminum aircraft fly at 40,000 feet or spacecraft orbit Earth, they do so because Alfred Wilm accidentally left a metal sample on his desk over a weekend in 1906. And because Alcoa metallurgists in 1917 to 1922 cracked the mystery of why that sample hardened. The technology is now so commonplace, we forget it was once impossible. Age-hardening aluminum alloys are standard engineering materials, specified routinely in thousands of applications. But in 1917, they were German military secrets America desperately needed and couldn't obtain. Alcoa didn't steal Duralumin, they created their own version through systematic research and scientific understanding. 17S/2017 was America's independent achievement, developed under wartime pressure by metallurgists who transformed theoretical insights into industrial-scale production. That alloy, refined and improved but fundamentally unchanged, still holds aircraft together today. Every rivet, every fastener, every structural member descended from Blough's 1922 formulation proves that material science, properly applied, can be as revolutionary as any invention. America had no aviation aluminum in 1917. By 1922, it had 17S, an alloy so successful it's manufactured today, over a century later, still enabling the skybound civilization Wilm and Blough made possible. The age of aluminum began in a German laboratory in 1906 and reached American industry in 1922. Everything that flies today owes something to that journey from accidental discovery to industrial achievement, from Duralumin to 17S to the millions of tons of age-hardened aluminum keeping aircraft aloft worldwide. Simple chemistry, precise metallurgy, transformative impact. That's the power of material science and the legacy of Alloy 2017, the aluminum that built the sky.